All right, y'all, this is going to be our run through for our Flipgrid activity, and we're going to be focusing on maximizing the volume of a box. So let me just kind of run through all the things that we're going to look at. A flat rectangular piece of cardboard has a length of 30 centimeters and a width of 20 centimeters. It is folded into a box. Oh, rectangular prism, ... All right, so what we're going to do is we're going to start by drawing our diagram, and we start with a two-dimensional rectangle. And on that two-dimensional rectangle, I'm going to go ahead and mark that we have a length of 30, and then we have a width of 20. Now, if you recall from our previous activities, we go ahead and take out a square in each one of those corners. And the reasons why we take out a square in each one of those corners is because we are going to fold along those sides in order to make a three-dimensional box. And since we are cutting out a square, we're cutting out the same size square every single time. We decided that we'd call those lengths of that square X. And it was easy to come up with our sides of the square once we cut that out as saying 20 minus 2x and 30 minus 2x because we were cutting out two x's. At that point, we were able to fold them up along those orange dotted lines there. And from there, we were able to say, well, we can make a three-dimensional figure or rectangular prism in this case. And as we did that, we would draw out our rectangular prism. Okay, and then we were able to label our dimensions. So we were able to say, okay, well, we've got 30 minus 2x. We had 20 minus 2x. And the really important part is that we represented that we were folding up. These would fold up to meet, and that would give us our height. Okay. Once we knew that, we were going to try to maximize our volume by developing a volume equation, which we all know the volume of a rectangular prism is simply length times width times height. But in this situation, we have binomials that represent the length and the width, and a monomial that represents the height there. So we're just going to say the volume of this equation is not just length times width times height. We'll say that v of x equals to 30 minus 2x, 20 minus 2x, and then we've got a height. Now, of course, we're going to jump over to Desmos and we're going to make a graph of this. That's going to be the thing. So you can see I've already typed it in. And what we want to do is we want to adjust our screen so we have a nice looking graph. So I'm going to grab that y-axis on Desmos. I'm going to pull down until I see exactly what I'm looking at. And then I'm going to do that with the x-axis, and I'm going to adjust that graph until I get a really nice view of what's happening here. Okay, now we do have a cubic graph, and it does go on the end behavior up to infinity and down to negative infinity. So we have to make some really good thought process towards what is the height, which is our x, that will create the maximum volume. Now, a lot of people want to say, well, the maximum volume's got to be over here. But it can't be over here because we can't take any piece of paper and it just keep growing and growing and growing and growing. There's got to be a cutoff point for that maximum volume. Well, remember, these are x's down here. These are our x's down here. And that tells us how much we're cutting out of the side of our piece of paper. And so, or cardboard. And so if I cut out 10 from this length, you can see it right there. If I was to cut out 10, it would actually just cut off the whole entire side and we would no longer be able to form a box. If you look at that here, check out what happens. The volume of this box comes back to 0 at 10 because that's the part where we cut off the whole entire side. And from here on out, these are all fake. They do not exist. Do not exist. All of our real boxes, or rectangular prisms in this case, are going to be from here to there along that graph. So what is the domain of real boxes? Well, we can start at 0. We can start at 0. We can go all the way to 10. But if we don't cut out anything, if we cut out 10, we don't have real boxes. So our domain of real boxes would be from 0 to 10. in this area. So I'd say, okay, well, the domain would be from 0 to 10. That would create real boxes. Okay. Let me go back in on our Desmos. I'm just going to go ahead and plant that on there real quick. Our domain of real boxes would be 0 is less than x is less than 10, or 0 to 10 in interval notation. And then what I'm going to do is I'm going to go ahead and find the max height and the max volume just based off of what we already know. So let's go ahead and clear all this stuff out. I'm going to click on that point, 3.92 and 1056.3. And we know that the maximum height is 3.92 centimeters. And we know that the maximum volume is 1056.3 cubic centimeters. Now, the last thing I want to do is I want to find all those dimensions. That's going to be our last piece right here. We know that the max height is 3.92. So let's go ahead and find the rest of the dimensions. How do we do that? We just simply type in our binomials. 330 minus 2 times 3.92. And we also do 20 minus 2 times 3.92. Now, when we get that, we get 22.16 and we get 12.16. And those are going to be our maximized dimensions. We can add those on to our class kick right there of 22.16. Let me change the color so we can see it. 22.16 times 12.16, which is our width. And then, of course, we've got our 3.92 that we originally found. All right, y'all, that's going to be our Flipgrid kind of outline for what we're doing for finding the maximized volume of a rectangular prism from a two-dimensional piece of material. Hope that helps y'all organize your thoughts towards this project.